Namaste and welcome to yet another lecture on mathematical foundations for machine learning. We were looking at the ideas of optimization. In the last class, we looked at unconstrained optimization problems, and now we want to look at constrained optimization problems where I'm going to put certain limitations on the the constraint. In fact, we looked at one example problem in the last lecture where we said that look, I have to maximize f of x comma y, and then subject to the constraint that I had x plus y is equal to 100. So I already know what it is. That means I have a objective function and I want to optimize it within a boundary. So that's the condition that I have, right? I have x comma y, I mean x plus y is equal to 100. That's basically a straight line that you have. So you're going to do this business, right? Now the question is, if I have a multivariate function, which is essentially what we will see in most of the machine learning problems, you have multivariate functions. How are we going to look at, see, if you look at the example that I have that I did in the previous class, which is basically f of x y is equal to x y, then maximize f of x y is equal to x y, and then subject to the constraints x plus y is equal to 100. I turned this two variable function to a single variable function, and then I did it, right. Now suppose if I have multivariable function and where it's not easy to have a constraint which is like this, how are we going to work? And the point is, like, what is it to say the second derivative test here? In this case, d square f by dx square, we got it, and it's easy because it was a single variable function. It turned out we converted the two variable function to a single variable function, and then we did this. Now if we are going to look for a maxima or minima with a multivariate function, how are we going to look at the second derivative? What is this to say second derivative test, and how do we do this? And is there any other way of solving a constraint optimization problem by looking at it in a different way? So that's what we are going to do. We are going to look at the idea of Lagrangian multipliers in today's class, and we are also going to look at optimizing an objective function with respect to multiple variables, right. So we are going to look at that. So let's take a simple example, let, and for this part of the course I am trying to follow the open textbook that you have at math LibreText Mathematics, where we have the ideas of constraint optimization and unconstrained optimization. The material is pretty interesting to look at, so I thought I would adopt that, though it is not specified in the what do you call the course the contents, the textbooks and the references mentioned in the course page. I would be referring materials available in the LibreText Mathematics, where we look at calculus book and where we talk about optimization and multiple variables and stuff, right. So that's the I'll be putting the textbook towards the end of the lecture so that you could also look at it. So that's what I'm going to do, right. Okay, so let's look at it. Suppose we have this following, suppose, or let f of x comma y, or f of x comma y be a real valued function. Remember, this is basically what we said as this is going to map R2 to R. It's going to map R2 to R. So this is what we had, and what we are going to say is let x naught comma y naught be a point in the domain of f. X naught y naught be a point in the domain of f. So what we are going to do, we are going to define what is it to say. First of all, we need to know what is it to say a maxima and what is it to say a minima. So we are going to define that first of all. So we are going to say that f is said to have a local, if said to have local maxima at x naught comma y naught if f of, let us say, any x comma y is less than or equal to f of x naught comma y naught. And we are going to put a constraint here. We are going to say it is not a question of constraint. That means we are going to say some in the neighborhood of this the point x naught comma y naught. So we are going to say for all x comma y in the neighborhood of x naught y naught. So what you basically say is you have a disk of, say, some positive radius and which is centered at, let us say, x naught comma y naught, and what we say is like you have a small r greater than 0, which is typically what we say epsilon greater than 0. So what we say that such that this f of x comma y is less than or equal to f of x naught comma y naught. So that is what we are going to say. Okay. So in the neighborhood of x comma y naught, x naught comma y naught. So how are we going to define this? We are going to say that for all x comma y in the neighborhood, that is inside some disk of, let us say, positive radius centered at x naught comma y naught. What do we mean by that? Again, this implies there is a sufficiently small r, there is some sufficiently small r greater than 0 such that f of x naught x comma y is less than or equal to f of x naught comma y naught for all x comma y for which x minus x naught the whole square plus y minus y naught the whole square is less than r square. You can also talk about the minima. If we talk about the minimum, we say that f has a minimum. So f has a minimum at x naught comma y naught if f of x comma y is greater than f of x naught comma y naught for all x comma y inside a disk, inside a disk centered at x naught comma y naught. Right. Okay, and this is basically we will call this as a local minimum, and we will call that as a local maxima. So this is local maxima and this is local minimum, and we are going to say global maximum and global minimum is like you take the entire domain of f. So if you are going to satisfy this condition, f of x comma y is less than or equal to f of x naught comma y naught, you have a global maximum at f of x naught comma y naught, and the other side. If it is going to be in the entire domain, if you are going to have f of x y to be greater than f of x naught comma y naught, you say that f has a minimum at x naught comma y naught, right. Okay, so how are we going to look at this? Like, we in the single variable case we had the idea of first derivative and second derivative test. Now when I have multiple variables here, I have to get to the idea of gradients. I have to collect the partial derivatives, equate the partial derivatives to 0, and then look for something in the second derivative. But equating the partial derivative to be to 0, what does that actually mean? Gradient equal to 0 means what? We are looking at level curve there. Remember, whenever we say gradient is 0, we are going to look at a level curve. So let us write that. Okay. So we are going to see this. Let f of x comma y be a real valued function such that the partial derivatives dou by dou x of f of x naught comma y naught and dou by dou y of f of x naught comma y naught, right, both exist. Then the necessary condition that we have, then the necessary condition for a local minima or a maxima for f of x comma y to have a local minima or a local maxima at the point x naught comma y naught is this. What is that? The gradient of the function f at x naught comma y naught is equal to 0. There is no surprise in this, because that is exactly how we define our when we want to talk about maxima or minima, or in the single variable case we want the first derivative to be equal to 0, which is basically what we call as the critical point, right. So we are going to say this, the point so the point x naught comma y naught x naught comma y naught where the gradient is 0, gradient f of x naught comma y naught is equal to 0 is called the critical point of the function, is called the critical point of the function. The critical point of the function, right. So you just need to do the partial derivatives, equate the partial derivative 0, so you will end up getting the what do you say, you end up getting the critical point. But there is one problem here. What is the problem? That at this point there may be I mean it is like necessary okay, this is a necessary condition, but it may not be sufficient. So you do not have a sufficient I mean what would you say is this you have necessary and sufficient conditions and various other things which you have studied. So gradient of f at the point x naught comma y naught equal to 0 is not always sufficient. It does not guarantee that there is that the critical point is going to be a local minima or local maxima, and that is going to depend on the you have to do a second derivative test, right. You have to do this. Okay, so what are we going to do? We are going to make the statement. So gradient of f at x naught comma y naught equal to 0 is necessary but not a sufficient condition to guarantee to guarantee that the critical point is a maxima or minima, right, is a local maximum or minimum. This is what we have seen even in the single variable case, where I mean it does not guarantee you to have a local maxima or a minimum. So, what are the conditions for sufficient conditions for a critical point to be the local maxima or minima of a smooth function? So, let us write this. So, the sufficient conditions for a critical point to be a local maxima or a minima, local maxima or a local minima. Okay, so what are the conditions? Let us look at the conditions. Number 1, let us define this. First of all, let us say this: f of x comma y be a smooth real valued function with critical point at, let us say, x naught comma y naught. What does this mean? That is, the gradient of f at x naught comma y naught is 0. Now, what we do is we are going to define. So, we define d is equal to dou square f by dou x square at the point x naught comma y naught into dou square f by dou y squared at the point x naught comma y naught minus dou square f by dou x dou y at the point x naught comma y naught the whole square. We are going to define d. Okay. Then we have the following. The necessary conditions are: A, if d is greater than 0 and dou squared f by dou x squared at x naught comma y naught is greater than 0, then we have a max. Oh, sorry, we have a local minimum. We discriminant this, we call it as discriminant or determinant, which is greater than 0, then we have then we say f has a local minimum at x naught comma y naught, right. The second one, if d is greater than 0 and dou square f by dou x squared at x naught comma y naught is less than 0, then f has local maxima at x naught y naught. Then the third point, we have C, this is C, if d is less than 0 and if first of all if t is less than 0, then we say that then f has neither local maxima nor minima, local max nor min, local minima at x naught comma y naught. So, we have covered greater than 0, then less than 0. The one important fellow who is left out is basically our dB equal to 0. This implies we are going to define this, we say that the test fails. And at the point where a comma b or this x naught comma y naught where d is less than 0, this point is basically what we call as saddle point, which is neither a maximum nor a minimum. Now, if you look at d, it reveals something very interesting. What is that? D is defined as dou squared f by dou x squared evaluated at x naught comma y naught into dou squared f by dou y squared evaluated at x naught comma y naught minus it said dou squared f at x naught comma y naught divided by dou x dou y the whole square. This is how we define D. If you look at it very carefully, it reveals something else. What is that? This looks like it is determinant of a 2 by 2 matrix. Now, what is the 2 by 2 matrix? Let us put all those elements, check what is that. This is going to be dou square f of x naught comma y naught divided by dou x squared. This is going to be dou squared f of x naught comma y naught by dou y squared, and here you have dou squared f of x naught comma y naught by dou x dou y, and this matrix is symmetric. So, that is why it says squared. So, I am going to write this as dou square f of x naught comma y naught divided by dou x dou y. Now, what is this matrix? We have seen this matrix already. What is this matrix? Yes, that is basically the Hessian matrix whose determinant is basically D. So, basically we are going to say D is equal to the determinant of the Hessian, right. This is what we have. So, determinant of the Hessian. So, you see that the Hessian comes into picture now. Second derivative test, we see that okay fine, Hessian is already there, right. So, what we are going to say is we are going to look at this. If Hessian is going to be positive definite, then you have local minima at that point, let us say x naught y naught. If the Hessian is going to be negative definite, then you are going to have a local maxima. When you are going to have the Hessian to be negative, in the sense the determinant is negative, then you are going to have neither what do you call a maxima nor a minima. In fact, if you look at the idea of positive definite, positive definite and negative definite, it is also related to the eigenvalues. It is basically defined on the eigenvalues, where you say a matrix is said to be a real symmetric matrix is said to be positive definite if the eigenvalues of the matrix, all the eigenvalues are positive, positive semi definite if all the eigenvalues are greater than or equal to 0, negative definite if the eigenvalues are all less than 0, negative semi definite if the eigenvalues are all less than or equal to 0, and if the eigenvalues are both positive and negative, then you call that matrix to be indefinite. So, when we want to have a local minimum, the Hessian matrix that you are going to look at must be a positive definite matrix, right. Great. Now, what you are going to do is okay, so let us probably take a quick example and see if you are able to appreciate this idea and see whether there is going to be a local maxima and minima. How do we compute all that? Let us take a simple example. So, let us look at this. Let us look at an example. So, we are going to say find all local maxima and local minima of f of x comma y is equal to x squared plus xy plus y squared minus 3x. Now I know this, I just need to find out the gradient of this. Del f is equal to 0. So I will write this del f is equal to 0. So what is del f? That is a gradient. So I have dou by dou x of f, which is nothing but 2x plus y minus 3, and dou f by dou y, which is nothing but 2y plus x. Now we have this 2x plus y minus 3 is equal to 0 and 2y plus x is equal to 0. So basically these two are two linear system of linear equations. You have 2x plus y is equal to 3 and x plus 2y is equal to 0. So you can, so the values, if you solving we get x comma y to be equal to 2 minus 1, and since it is a linear equation, just have one point which is there, that is the point of intersection. So this is going to be the only critical point. This is going to be the only critical point. Now what you do is you look at the second order partial derivatives here. So I have dou squared f by dou x squared, which is nothing but 2, dou squared f by dou y squared, which is again 2, dou squared f by dou x dou y, which is nothing but 1. Then I have dou square f by dou y dou x, right, that is also equal to 1. So these two are the same. So what we have is we have the our matrix to be this. So our Hessian is going to be 2 2 1 1, and the determinant of this is basically 4 minus 1, which is 3, right. Now but we really do not know if this matrix is positive, definite or what, because the determinant is 3. You know that the determinant of the matrix is equal to the product of the eigenvalues. This is a positive number. So positive number you can obtain when you know that it is the product of eigenvalues. Both eigenvalues can be negative or both eigenvalues can be positive to give you this determinant, which is plus 3. So we need to check using our test whatever that we have had, where we computed this what we call, we had this discriminant, and we also wanted to look at so this discriminant is greater than 3 or the determinant is greater than 3. Now what we want to do is the first condition, if you look at the first condition that we wrote, it says d is greater than 0, that we found out. We also want to find out if dou square f by dou x square at x naught y naught is greater than 0. So dou square f by dou x square is 2, which is already there, which is greater than 0. So we have dou square f by dou x square at what is the critical point, 2 comma minus 1. Anyway, it is a constant value that you get, which is 2. This implies the determinant is greater than 0 and dou square f by dou x squared at 2 minus 1 is also greater than 0, which means we have a local minima. We have a local minima at x is x comma y is equal to 2 comma minus 1, right. So we have a local minima there. Now where are we going from here? Okay, we have looked at the, we brought in the idea of Hessian matrix here, where we look at second order partial derivative and second order test derivative, second order derivatives test we have done, and we get this to be local. We decide whether you are going to get a local minima or local maxima, or you are going to get a saddle point. at that particular value of say x naught comma y naught by looking at the determinant of the Hessian and so on. Now, having done this, I will probably continue with the idea of Lagrangian multiplier for converting a constrained optimization problem to an unconstrained optimization problem in the next lecture, and then we will take the idea of PCA and least square solution. So, when we come back in the next lecture, we are going to look at the idea of Lagrangian multiplier. We are going to look at Lagrangian multiplier for converting a constrained optimization problem to an unconstrained optimization problem, followed by PCA and we will do least squares first and then look at PCA. And towards the end of this, after we do all these things, we have mathematically found out like what is the minima, what is the maxima, and what are the parameters which would give me that minima, what are the parameters which would give me that maxima, which is precisely what we will do in terms of our cost function, optimizing the cost function in terms of your model parameters in machine learning. What we will do is, we have numerically got this number, we have actually worked out and then we have got these numbers. Now, how do we get this number algorithmically, and that is where gradient descent algorithm comes into picture. We look at gradient descent algorithm in detail, which is what Gaurav Hegde will be teaching you. Namaste.